Hello everyone, welcome to Sujaya Chem classes. Today we will continue with the question answer discussion from the unit Electrochemistry, and this is a continuation of what was already done in part 1 and 2. So let's start with question number 1. The molar conductivity of 0.05 molar aqueous solution of formic acid, also called as methanoic acid, was measured as 4.61 Siemens meter square per mole. What is the pKa value of the acid? Remember, formic acid is a weak acid. What is given? Lambda naught H plus. The molar conductivity at infinite dilution of hydrogen ions is given 34.96 Siemens meter square per mole, and that of methanoate or formate ion lambda naught H COO minus is given as 5.46 Siemens meter square per mole. 4 options are given. We need to work out and then choose the right option. So, to solve this problem, we need to follow 4 steps. The first step is calculation of molar conductivity of formic acid at infinite dilution, that is lambda naught M of HCOOH. Step 2 would be from this value and given lambda molar conductivity value at the given concentration, we can calculate degree of dissociation alpha. The third step would be calculation of ionization constant Ka of the weak acid, methanoic acid. Then the last step would be calculation of pKa value, which is equal, the mathematical expression of which is pKa is equal to minus log Ka. So from the given data we need to work out step by step. First step, calculation of molar conductivity at infinite dilution of formic acid. That can be done by finding the sum of molar conductivity of both the cation and anion at infinite dilution. When we add it, that is 34.96 plus 5.46, we get as 40.42 Siemens meter square per mole. Second step, calculation of degree of dissociation, which is alpha. Alpha is equal to molar conductivity at the given concentration divided by molar conductivity at infinite dilution. In the problem, it is given that the molar conductivity of 0.05 molar solution is 4.61 Siemens meter square per mole. So substituting molar conductivity at the given concentration as 4.61 divided by molar conductivity at infinite dilution, we have calculated it as 40.42. Dividing it, we get alpha, degree of dissociation, is equal to 0.1141. Step 3. Using this alpha value, we need to calculate the ionization constant Ka of the weak acid, which is formic acid. We know the formula. Ka, the ionization constant of a weak acid, is C alpha square divided by 1 minus alpha. Substituting the value of C as 0.05 as given in the problem into alpha square 0.1141. I have the last decimal digit I have neglected. So 0.114 the whole square divided by 1 minus alpha, 1 minus 0.114. When on calculating it, we get it to be equal to 0.00073334. Therefore, shifting the decimal towards the right, we get Ka is equal to 7.334 into 10 to the power minus 4. The last step is calculation of pKa value of the acid. pKa is equal to minus log Ka. So substituting the Ka value, minus of log of 7.334 into 10 power minus 4. Taking the minus sign outside and taking the log, we get minus 4.0000 plus log of 73 in the third column, mean difference 4 is 0.8653. Removing the negative sign and the brackets, we get it as plus 4.00 minus 0.86 minus 0.8653, correct, which is equal to 3.1347. So pKa value is calculated to be 3.1347. So if you look at the options, option B would be the right answer. Question number 2. In which one of the following pairs M bar Mn plus combination, that is metal bar metal ion combination, the second can be reduced by the first? Four options A, B, C and D are given. You look at the options. Al3 plus bar Al and Mg2 plus bar Mg. B. Ca2 plus bar Ca and Sn2 plus bar Sn. C. Ag plus bar Ag and Cu2 plus bar Cu. D. Pb2 plus bar Pb and Cr3 plus bar Cr. To answer this question, a student should have some knowledge of where these metal ions lie, metal ion combination lies in the electrochemical series. I have gone straight to the answer. I have taken the standard reduction electrode potential of Sn2 plus bar Sn. That is E0 reduction potential in the standard state is minus 0.14 volt and that of Ca2 plus bar Ca is minus 2.87 volt. Therefore, if you look at these values, the standard reduction electrode potential of calcium 2 plus bar calcium is largely negative. It has a high negative value. Therefore, larger the negative value of the standard reduction electrode potential, stronger would be its reducing action. Therefore, Ca2 plus bar Ca is a strong reducing agent which can readily reduce Sn2 plus to Sn metal. Therefore, option B is the correct option. If you look at options A, C and D, the second metal ion cannot be reduced by the first metal ion combination, that is Al3 plus bar Al cannot be combined with Mg2 plus bar Mg. Why, if you ask? Because the standard reduction electrode potential of the second one, Mg2 plus, has a larger negative value than that of Al3 plus. Similarly for C and D. Therefore, option B would be the right choice. Question number 3. Which one of the following can be used to compare the conductivities of electrolytes? A. Specific conductivity, that is kappa. B. Conductance, which we can represent by the symbol G. C is molar conductivity, lambda m. And D is resistivity, which is rho, RHO, rho. Now, to answer this question, we need to remember that conductivities of electrolytes are greatly influenced by the concentration. So, you choose that factor in whose mathematical expression the concentration term comes. If you look at the mathematical expression of specific conductivity, kappa, K is equal to G into L by A. There's no concentration term. Conductance, Similarly, G, conductance is equal to 1 by R, which is equal to A into rho by L, where A is the area of cross section of the electrolyte, rho is the resistivity, and L is the length of the electrolyte. There is no concentration term in its mathematical expression. Consider molar conductivity. Lambda m is equal to 1000 kappa by C, where C is the concentration of the electrolyte. So see, in its mathematical expression, concentration term has been added. Therefore, we can choose molar conductivity as the correct factor which can be used to compare the conductivities of electrolytes. What about resistivity? Resistivity rho is the resistivity is given the symbol rho. Rho is equal to we can say that first we give the expression as such. R, the resistance of an electrolyte, is equal to rho into L by A. Therefore, rho is equal to R into A by L. There is no concentration term. Therefore, molar conductivity is the right choice to compare the conductivities of electrolytes. Then, in case of why, if you ask why concentration, because if you take the same electrolyte, say for example KCl, if two solutions of KCl, same electrolyte, has different concentrations. In one case it is zero point 0.1 molar, in the other case it is 0.75 molar. Their conductivities would be different. They would have different conductivities. The same electrolyte with different molar concentrations would show different conductivities. Therefore, option C is the correct answer. Question number 4. For the cell reaction 4Br minus plus O2 plus 4H plus gives 2Br2 plus 2H2O at 298 Kelvin. The E0 cell is equal to plus 0.16 volt. What would be the K dash equilibrium constant value if the reverse reaction were to take place? Because it is calculation of equilibrium constant for the reverse reaction, it is shown by the symbol K dash C. So 4 options are given. We need to work out and then choose the right option. If you look at the cell reaction taking place, bromide ions are getting oxidized to bromine gas and H plus ions are getting reduced to water. So 4Br minus loses 4 electrons and 4H plus picks up these 4 electrons to get reduced to water, while Br minus gets oxidized to Br2. So therefore, in this cell reaction, the involvement of 4 electrons is seen, or in other words, N is equal to 4, the number of electrons. So this problem can be solved in 2 steps. First step is calculate E0 cell, and second step, use it, reverse the E0 value and use it to calculate K dash C, the equilibrium constant for the reverse reaction. What is the reverse reaction? 2Br2 plus 2H2O giving 4Br minus plus O2 plus 4H plus. That is the reverse reaction. So, let's start with the calculation part. For the given reaction, E0 cell value is given as plus 0.16 volt. Therefore, for the reverse reaction, E0 cell would be minus 0.16 volt. Magnitude would remain the same, only the sign would change. So if it is E naught cell is plus 0.16 volt for the forward reaction, it would become minus 0.16 volt for the reverse reaction. Therefore, next step is using the formula E naught cell is equal to log K dash C into 2.303 RT by NF, or E naught cell is equal to log K dash C into substituting the value of R as 8.314 joules per Kelvin per mole, temperature 298 Kelvin divided by F 96,500 coulombs, we get it as 0.059 divided by n. So E naught cell is equal to log K dash C into 0.059 by n. Substituting the value, or log Kc is equal to E naught cell into n by 0.059, because n is given as 4. So it would become 4 into, I put a star mark for into, 4 into E naught cell is minus 0.16 divided by 0.059, which is equal to minus 10.847. So log Kc works out to be a negative number, minus 10.847. Before taking the anti-logarithm, we need to convert it into characteristic and mantissa. Mantissa can never be negative. So I have given, first let us see the calculation of how to take the antilog of a negative number. For example, here we got log K dash C as minus 10.847. So K dash C would be antilog of minus 10.847. How to take the antilog of minus 10.847? First, you must convert this negative number into characteristic and mantissa form before using the anti-logarithm table. For that, you need to add and subtract 1 to make the mantissa positive. So, antilog of minus 10.847 is equal to minus 10 plus of minus 1 plus 1. Minus 1 minus 10 would become minus 11. Plus 1 minus 0.847. Still the characters mantissa is negative. So you are subtracting it from 1. 1 minus 0.847 is 1.153. Therefore, we get the number is now ready for taking the antilog. Taking antilog of minus 11.153, we get it as 1442 and minus the characteristic is minus 11. So we can write the value as 1.422 into 10 power minus 11. 1.42. After one digit, put the decimal and into 10 power minus the characteristic number. So, the correct answer of K dash C, the equilibrium constant for the reverse reaction is 1.442 into 10 power minus 11. You will come across such antilog of negative numbers usually in the calculation of equilibrium constant. So be careful while calculating it. Question number 5. Match the commercial cells listed out in column 1 with the corresponding electrolytes given in column 2. In column 1, WXYZ. That's the serial number of the cells given. W mercury cell, X fuel cell, Y dry cell, Z lead storage battery. Then column 2 electrolytes are listed out. PQRS. P is aqueous KOH, Q aqueous sulfuric acid, R paste of KOH and zinc oxide, S paste of ammonium chloride and zinc chloride. So we have to match the commercial cells listed out with the corresponding electrolytes in them. It's a simple question. So W mercury cell, the electrolyte is R, paste of KOH and zinc oxide. X fuel cell, the electrolyte is aqueous KOH. Y dry cell is S, paste of ammonium chloride and zinc chloride. Z lead storage battery, which is a secondary cell, is the electrolyte is Q, aqueous KOH. Question number 6. Two statements, assertion and reason are given. Choose the right option for the assertion and reason statements given. The options are A. Both assertion and reason are correct, and reason is the correct explanation for assertion. B. Both assertion and reason are correct, but reason is not the correct explanation for assertion. C. Assertion is wrong, but reason is correct. D. Assertion is correct, but reason is wrong. The statement assertion. The limiting molar conductivity of a weak electrolyte can be directly measured experimentally. Reason. The limiting molar conductivity of a weak electrolyte at infinite dilution can be calculated only from the lambda naught plus and lambda naught minus values of a weak electrolyte. That is, the lambda naught plus value of the cation and anion. These values for a strong electrolytes have to be substituted for the weak electrolyte, corresponding weak electrolyte, and calculated, not experimentally determined, is what the reason states. So we need to choose the right option. The answer is assertion is wrong, but reason is correct. The limiting molar conductivity of a weak electrolyte cannot be directly measured experimentally. Why? Due to very low concentration of ions at infinite dilution. For weak electrolytes, therefore, the limiting molar conductivity is indirectly determined using the lambda naught plus and lambda naught minus values of strong electrolytes and applying Kohlrausch's law of independent migration of ions. Therefore, option C is correct. Here I have given by the side a graph showing the variation of lambda m versus square root of concentration for a strong and weak electrolyte. These values are based on experimental findings, observations. So for weak electrolyte, if you look at the graph, it goes almost parallel to the molar conductivity axis. So therefore, experimentally, it is not possible to find out the limiting molar conductivity of a weak electrolyte. It can only be determined from the lambda naught plus and lambda naught minus values of strong electrolytes using the correct cation and anion present in the weak electrolyte. Question number 7. Given are 4 commercial cells with the electrochemical reactions occurring in these cells. 2 of the reactions shown as taking place in the cells are incorrect. Identify the 2. A. Lead storage battery. At cathode, lead solid plus 2 sulfate ions plus 4 hydrogen ions plus 2 electrons give lead sulfate solid PbSO4 plus 2H2O plus SO2 gas. B. Leclanche's cell. It is also called as dry cell. At cathode, MnO2 plus NH4 plus 2 electrons give MnO plus OH minus plus NH3. C. Mercury cell. At anode, Zn bar Hg, which is zinc amalgam, plus 2 OH minus gives ZnO plus H2O plus 2 electrons. At anode, oxidation is seen. D. Fuel cell. At cathode, O2 gas plus 2 H2O plus 4 electrons give 4 OH minus. Four options are given. We need to choose which of the two electrochemical reactions shown as occurring in the cells at either cathode or anode is wrong. We have to identify. So, if we look at these four electrochemical reactions, A and B are wrong reactions. The corrected reactions are shown. In the lead storage battery at cathode, PbO2 plus SO4 2 minus plus 4H plus 2 electrons give lead sulfate solid plus 2H2O liquid. It's the reverse of the reaction which is shown as A. And B, in the dry cell or Leclanche cell at cathode, MnO2 plus 4H plus NH4 plus 1 electron gives MnOOH. It's a compound plus NH3. So A and B are wrong reactions. Option A is correct. Here I have shown a diagram of Leclanche cell which looks better than the one given in the textbook. You just see that diagram. Question number 8. Two statements, one assertion and the other reason are given. Choose the correct option. Assertion. During the electrolysis of aqueous NaCl, that is brine solution, chlorine is liberated at the anode in preference to oxygen and water gets reduced to hydrogen at the cathode. E0 Cl minus bar half Cl2 is plus 1.36 volt and E0 H2O bar O2 is plus 1.23 volt. Reason. The reaction at anode with lower oxidation potential is not preferred due to over potential of oxygen. The options are slightly different. Assertion is correct, but reason is incorrect. B. Assertion is incorrect, but reason is correct. C. Both assertion and reason are correct. D. Both assertion and reason are incorrect. Now, if you look at the E0 values, E0 Cl minus giving half Cl2. If you look at that, it is the oxidation potential values which are given. Cl minus is oxidized to half Cl2 gas and water, the oxide ion of water is oxidized to oxygen. So, in this case, if you look at the oxidation potential, that of water getting oxidized to oxygen is lower. So that reaction should be taking place at the anode. The oxidation potential of water is less than that of Cl minus. So at anode we expect not Cl2 gas but oxygen gas to be liberated. At anode, the reaction with lower oxidation potential should have occurred and water should have got oxidized to what? To oxygen in preference to Cl minus. But what is actually seen experimentally, it is found that at anode, Cl2 gas gets liberated. Why? The reason is on account of overpotential of oxygen. It is chloride ions which get oxidized to chlorine at the anode. More about overpotential you will be studying in higher classes. So, the overall reaction occurring in the electrolytic cell is 2 NaCl, that is aqueous NaCl means there's water. So plus 2 H2O gives 2 Na plus aqueous plus 2 OH minus aqueous. That means the electrolyte now has Na plus and OH minus. That means caustic soda is formed. Sodium hydroxide is formed in the electrolyte. And what is liberated at the cathode? Hydrogen gas. At the anode, chlorine gas. So, hydrogen gas gets liberated at cathode, chlorine at anode, alongside with formation of NaOH in the cell. Therefore, option C is correct. Both assertion and reason are correct. I have given a diagram of a cell showing electrolysis of brine solution, NaCl solution. Question number 9. When 0.1 mole per liter of KCl was filled in a conductivity cell, the resistance of the cell was 90 ohms at 298 Kelvin. Conductivity of 0.1 molar KCl at 298 Kelvin is 1.29 Siemens per meter. The same cell, that means the same conductivity cell, when filled with an unknown electrolyte of concentration 0.03 molar, had a resistance of 96 ohms. What is the molar conductivity of the electrolyte at the given concentration? So we need to calculate the molar conductivity of the electrolyte which is filled in the conductivity cell. 4 options are given. We have to choose the correct option, right option. Now, if you look at this problem can be solved in 3 steps. First, we need to calculate the cell constant of this conductivity cell. Second, using the cell constant and the data given, we can calculate the conductivity of the unknown electrolyte. Once kappa, the conductivity of the unknown electrolyte, is calculated, third step would be calculation of its molar conductivity. So, first step, specific conductivity, that is kappa. You can call it as specific conductivity or conductivity. Kappa value is given. What is it equal to? 1.29 Siemens per meter. That has to be converted into centimeter. 1.29 Siemens per meter means divide by 100. So you get conductivity kappa is equal to 0.0129 Siemens per centimeter. Now, why do we have to convert it into centimeter? Because always cell constant is given in centimeter units. Now, what about the resistance offered by this KCl solution taken in the conductivity cell? 90 ohms. So, to calculate the cell constant, which is L by A, kappa is equal to G into L by A. What is G? 1 by R. G is equal to 1 by R. Substitute the value of R as 90. So we get kappa 0.0129 is equal to 1 by 90 into L by A, where L by A is the cell constant. Therefore, L by A is equal to 0.0129 into 90, which is equal to 1.161 per centimeter, the unit for cell constant per centimeter. So, we have calculated the cell constant of the conductivity cell. Now, this cell is cleaned, washed, and now filled with the unknown electrolyte. The unknown electrolyte offers a resistance of 96 ohms. So, for this unknown electrolyte, we can calculate kappa, the conductivity, that is equal to G into L by A. We know the L by A value. We know G, how G is equal to 1 by R, reciprocal of resistance. So kappa is equal to 1 by 96 into L by A, which is 1.161. Multiply by 1.161. 1 by 96 into 1.161 is equal to 0.01209 Siemens per centimeter. That is the kappa value. Now, we know the kappa value of the unknown electrolyte. It's step 3 is simple. Calculate molar conductivity. Lambda m of the unknown electrolyte is 1000 into kappa by C. What is the concentration of the unknown electrolyte? Given 0.03. So substitute the kappa value 1000 multiplied by 1000 divided by 0.03, we get the molar conductivity to be equal to 403 Siemens centimeter square per mole. Therefore, lambda m, the molar conductivity of the unknown electrolyte, is 403 Siemens centimeter square per mole. Option A is the right answer. Question number 10. A galvanic cell functioning at 298 Kelvin has two hydrogen electrodes, meaning that both anode and cathode are hydrogen electrodes. The positive electrode, which is the positive electrode in a galvanic cell? The cathode. Okay, that you have to remember. The positive electrode is dipped into a solution of HCl whose H plus ion concentration is 10 power minus 2 molar. The EMF of the cell is 0.118 volt. What is the concentration of hydrogen ions at the negative electrode? Remember, in a galvanic cell, the negative electrode is the anode. So, the galvanic cell can be represented as half H2 gas bar H plus ion. Anode on the left hand side we have shown. The concentration of H plus ions at the negative electrode means at the anode. That's why I put a question mark. At the anode, what is the molar concentration of hydrogen ions? We need to calculate and find out. Then at the cathode, the H plus ions concentration is 0.01 molar bar half H2 gas. So both cathode and anode are hydrogen electrodes. The reaction taking place, the electrochemical reaction taking place at cathode, reduction. H plus ions taking up electron getting reduced to H2 gas. At anode, oxidation. Half H2 gas minus 1 electron giving H plus at anode. Why I gave this electrochemical reaction? Just because we need to know the value of N. Here in this case, if you look at the overall cell reaction, it is N is equal to 1. 1 electron is involved in the redox reaction. Therefore, we can write, use Nernst equation. E cell is equal to E naught cell minus 0.059 by N log of concentration of electrolyte at anode divided by concentration of electrolyte at cathode. Since it is a hydrogen electrode, both the electrodes are hydrogen electrodes, so E naught cell would be negative. Therefore, E cell is equal to E naught cell, we can safely put 0, E naught cell as 0, 0 minus 0.59 by 1, N is equal to 1, log of molar concentration of H plus ions divided by concentration of H plus ions at cathode is 10 power minus 2. Then calculate. Therefore, E cell value is 0.118. 0.118 minus 0 is 0.118. So 0.118 is equal to minus 0.059 by 1. 1 is the end value. Log of H plus ions divided by molar concentration of the H plus ions at cathode 10 power minus 2, or log of H plus ions by 10 power minus 2 is equal to minus 0.118 into 1 by 0.059 minus 0.118 divided by 0.059 is minus 2. Therefore, we get log of H plus ions by 10 power minus 2 is equal to minus 2.000. Therefore, H plus ion by 10 power minus 2 is equal to anti-log of minus 2. Anti-log of minus 2 is 10 power minus 2. 10 power minus 2. Log of 10 to minus 2. Minus 2 anti-log will be 10 power minus 2. Therefore, we have got molar concentration of H plus ions by 10 power minus 2 is equal to 10 power minus 2. Therefore, H plus ion concentration is 10 power minus 2 into 10 power minus 2. Add the powers, you get H plus ion concentration is 10 power minus 4 moles per liter. That would be the molar concentration of H plus ions at the negative electrode, which is the anode. Question number 11. The E naught, that is M3 plus bar M2 plus. If you look carefully, it is the reduction potential. E naught values are the standard reduction potential values. The E naught values for 4 metals A, B, C and D are minus 0.41 volt, plus 1.57 volt, plus 0.77 volt and plus 1.97 volt respectively. Which one of these metals can most easily change from plus 2 to plus 3 oxidation state? If you look at the E naught values, they are all reduction potential values in the standard state. But if you look at the question, what you are asked, one of these metals, which one will change most easily from plus 2 to plus 3? That means they should get oxidized. You look at the values. I have written out the values with the E naught reactions. E naught M3 plus bar M2 plus for metal A minus 0.41. These are the reduction potential values. So also for metal B, C and D. If you look at the reduction potential values for metals B, C and D, the values are positive. But we know that the more negative the reduction potential value, stronger would be the tendency of that metal to act as a reducing agent, or in other words, stronger would be its tendency to get oxidized. Here, the oxidation would be from plus 2 to plus 3 state. So, among these 4 metals, metal A has negative value for its standard reduction potential, meaning this metal would show greatest tendency to get oxidized. From where? From plus 2 to plus 3 oxidation state. So since metal A has more negative value for the reduction potential, that is E naught M3 plus to M2, it will show greatest tendency to change over, means to get oxidized from plus 2 to plus 3 oxidation state. So metal A would show the maximum tendency, greatest tendency to get oxidized from plus 3 to plus 2 oxidation state. Question number 12. The standard reduction electrode potential values of 3 electrodes are given. E naught Mg2 plus bar Mg minus 2.36 volt. E naught Ni2 plus bar Ni minus 0.23 volt. E naught Fe2 plus bar Fe minus 0.44 volt. When would the reaction A solid plus B2 plus aqueous give A2 plus aqueous plus B solid become spontaneous? So, four options are given. A metal and B metal is given. You need to choose the correct metal as A and the ions as B, so that this reaction, the cell reaction A solid plus B2 plus aqueous giving A2 plus aqueous plus B solid becomes spontaneous. That means we need to go by E naught cell value. E naught for a spontaneous reaction, E naught cell value would be positive, and for a spontaneous reaction, the change in free energy delta G should be negative or less than 0. Now, here, if you see the reaction here, N is equal to 2. The number of electrons involved is equal to 2. So, from equation 1, we need to choose the metal which will show tendency to get oxidized readily. From the options given, suppose we choose magnesium metal as A and the combination with it is given as B. Magnesium metal as A and B nickel metal. Then substituting the value, E naught cell is equal to E naught cathode minus E naught anode. So what is our cathode? The cathode is nickel ions, bar nickel. So minus 0.23, minus 0.23. E naught cathode minus of minus E naught anode. E naught anode is minus 2.36 volt. So minus and minus becomes plus 2.36 volt minus 0.23 volt. We get E naught cell is positive plus 2.13 volt. If E naught cell is positive, that means the electrochemical reaction would result in electrical energy being produced. That means electrical work is done. Definitely delta G would be negative. Let us substitute this value in delta G naught mathematical expression. We know that delta G naught is equal to minus NF E naught cell. Substitute E naught cell value as plus 2.13 volt. Therefore, delta G naught is equal to minus N is 2 into F is 96,500 coulombs into E naught cell is 2.13 volt. Coulomb into volt will give us joules, the unit for work. So delta G naught is equal to minus 4 lakhs 11,090 joules of work is done. Since the values 4 minus 411090 joules of work is done. Since delta G naught is largely negative, it indicates that the cell is able to perform electrical work due to occurrence of spontaneous reaction, electrochemical reaction taking place in the cell. So our correct option would be option 4, where A is magnesium metal and B ions are nickel ions. For all the other combinations of, that is, metal, if A is nickel or B is magnesium, if A is iron and B is magnesium, if A is nickel and B is iron, for all these combinations we will get E naught cell to be negative. E naught cell will come out as negative. Therefore, delta G naught will become largely positive or greater than 0, indicating that these redox reactions are non-spontaneous. Therefore, options 1, 2 and 3 are incorrect. They cannot be chosen. They are not the right options. Option 4 is the correct answer. Question number 13. The net reaction taking place in an electrochemical cell is X solid plus Y2 plus gives X2 plus Y solid. The standard cell potential E naught cell value is 0.295 volt at 298 Kelvin. Calculate the equilibrium constant Kc for the redox reaction occurring in the cell. If you look at this question, it is a direct application of the formula E naught cell is equal to 2.303 into RT into log Kc by NF. That's all. In this case, we just need to know what is N, because NF, we have to know the number of electrons involved in the redox reaction. X solid is getting converted to X2 plus, that means loss of 2 electrons. Y2 plus is gaining 2 electrons and getting reduced to Y solid. So here N is equal to 2. Temperature 298 Kelvin. E naught cell value 0.295 volt and R is 8.314 joules per Kelvin per mole. So substituting in the equation or mathematical expression, E naught cell is equal to 2.303 into RT into log Kc divided by NF. Therefore, log Kc is equal to E naught cell into NF divided by 2.303 RT. Substituting values, we get log Kc is equal to 9.9784. So, log Kc is 9.9784. Therefore, Kc is equal to anti-log of 9.9784. Take the antilog of 0.97 in the 8th column, add mean difference 4. We get it as 9515. Put the decimal after one digit, that is 9.515 into 10 power 9, because it is 9.9. So, antilog of that is 9.515 into 10 power 9. That is the equilibrium constant Kc value for this reaction. Question 14. When an aqueous solution of common salt, that is brine solution, is electrolyte, the pH of the resultant electrolyte dash. We have to fill up the blank space. Already we have come across this electrolysis of brine solution. We have seen the equation 2NaCl plus 2H2O gives 2Na plus aqueous plus 2 OH minus aqueous plus H2 gas at cathode plus Cl2 gas at anode. Therefore, since in the electrolyte NaOH, a base is formed, the pH of the remaining electrolyte will increase. So the pH of the remaining electrolyte increases because caustic soda NaOH is formed, which is a base. Question 15. What happens to the pH of dilute sulfuric acid when it is electrolyzed? The pH of dilute solution of sulfuric acid remains constant on being electrolyzed. Why? Because the electrolysis process essentially involves electrolysis of water, while sulfuric acid just enhances the conductivity of the solution. So at the anode, which is the positive electrode in an electrolytic cell, OH minus ions get oxidized to produce oxygen gas and water. At cathode, which is negative in an electrolytic cell, what happens? H plus ions are reduced to produce H2 gas. So at anode, OH minus ions get oxidized to oxygen gas, while at cathode, H plus ions are reduced to produce H2 gas. Since the number of H plus ions reduced at cathode is equal to the number of hydroxide ions oxidized at anode, the overall concentration of H plus and OH minus in the electrolyte does not change significantly. Therefore, pH remains stable or constant. Now, there's a question which you have to answer. What would happen when concentrated sulfuric acid is electrolyzed? Question number 15. If the lambda naught m value, that is molar conductivity at infinite dilution value of acetic acid, is 390.5 Siemens centimeter square per mole, what is the dissociation constant of the acid if 1.028 into 10 power minus 3 molar solution of it has a conductivity of 4.95 into 10 power minus 5 Siemens per centimeter. So, lambda naught value is given, kappa is given, concentration is given. You need to calculate the molar conductivity of acetic acid at the given concentration. Lambda naught m value is already given as 390.5 Siemens centimeter square per mole. Now, we need to calculate lambda m. Why? Because we know that degree of dissociation alpha is the fraction of the electrolyte which is dissociated. We assume that a weak electrolyte like CH3COOH, acetic acid, gets fully ionized or dissociated at infinite dilution. So, lambda naught m represents the dissociation of acetic acid, which is completely dissociated. Therefore, the ratio between lambda m and lambda naught m will give us the fraction of the electrolyte which is dissociated, that is alpha, degree of dissociation. So it's a simple numerical, but here we have not touched upon degree of dissociation type of problems. So let's calculate lambda m. Lambda m at the given concentration, that is 1.028 into 10 power minus 3 molar, that is 1000 into kappa into C. So that 1000 into 4.95 into 10 power minus 5 divided by concentration 1.028 into 10 power minus 3, which is equal to 48.15 Siemens centimeter square per mole. What is 48.15 Siemens centimeter square per mole? Lambda m. Therefore, degree of dissociation alpha is equal to lambda m by lambda naught m. Remember, I told you lambda naught m is the molar conductivity at infinite dilution, which means that at this dilution, the weak electrolyte is completely dissociated or ionized. So, lambda m value is 48.15 divided by lambda naught m. See the large value 390.5 is equal to the fraction is equal to 0.1233. So alpha is 0.1233. That is the extent to which the electrolyte CH3COOH is dissociated. So in this part, we have completed 15 questions. Therefore, in the unit electrochemistry, totally we have completed discussion of 35 questions and answers. My next session would be question and answer discussion from class 11 unit structure of atom. I request students, those who are following my channels, Sujaya Chem classes, you can request your friends, you can invite your friends to follow my channel, and once they join you, you can have constructive discussion among yourself or between between friends, and get to learn better. So my request would be, please invite your friends also to join my channel. Thank you and regards to all of you. So let's next week or so I will be posting questions and answers from the class 11 second unit structure of atom.